Hello everyone. I, Mrs. Vineeta Philip, Assistant Professor in Department of Electronics and Telecommunication Engineering of AISSMS Institute of Information Technology Pune, welcome you all for my series of videos pertaining to important topics of the subject Signals and System for SE-ENTC Engineering 2019 pattern. In this video, I would be discussing the concept and practical demonstration of the third practical from the list of Signals and Control Lab of SE-ENTC 2019 pattern of SPPU. The title of the third practical is Sampling Theorem. What is sampling theorem? A band limited CT signal with highest frequency Fmax Hz can be uniquely recovered from its samples provided that the sampling rate Fs is greater than or equal to twice the maximum frequency of samples per second. That is, Fs must be greater than or equal to 2 Fmax. Here, Fs is equal to 2 Fmax is the Nyquist rate and the folding frequency is half the sampling frequency. For sampling a signal, a sample and hold circuit is employed which samples the signal at uniform time intervals called the sampling interval T. Now let us see some examples. In this example, the frequency of input signal is 40 Hz and the sampling frequency is 100 Hz, which is greater than twice the maximum frequency, that is 2 into 40, which is 80 Hz. As the sampling theorem is satisfied, we can get the original signal faithfully reconstructed. Here is another example. When the input frequency of the signal is 90 Hz and the sampling frequency is 100 Hz, we know that the minimum sampling frequency required for faithfully reconstructing the signal in this case is 2 into 90, which is 180 Hz. But here the sampling frequency is 100 Hz and the sampling theorem is not satisfied, leading to mismatch between the original signal and reconstructed signal. Let us now see a program in MATLAB to verify this sampling theorem. For the given t up to 0.5 with a step size of 0.00005 and length 0.5, we will plot our original signal defined by x2. Here, frequency f is equal to 50. The resultant plots of the signals are that of the original signal and the sample signal. So we take 2 rows, 1 column, and our original signal is plotted at the first position with the command subplot 2, 1, 1. And our this signal is plotted against time in red color. The x label of the signal is time index, y label is amplitude, and the title of the signal is time domain wave. Next, we want to plot the discretized version of our signal. So we have n 0 is to 1 by 80 is equal to 0.5. So here our frequency is 80. Using subplot command to plot this discrete signal in the second position, we use the command subplot 2, 1, 2. The stem command is used to discretize the signal, giving proper x labeling as discrete time index, y label as amplitude, and the title to this signal as time domain signal for insufficient Fs, which is 80 Hz taken here. Next, we intend to plot both these signals on a separate figure window for which we use the command figure. So the next command after the figure is plot, wherein we are going to plot each of these signals in the predefined colors and with proper X labeling as time index and Y label as amplitude, and the title to this figure as CT and DT signals on the same graph. Let us now observe the corresponding plots. We see that since the sampled frequency is 80 Hz and is insufficient, so the original signal is not faithfully reconstructed. This is called aliasing, and this effect is called aliasing effect. One way to mitigate this effect is by using anti-aliasing filter. That's all for now. Thank you for watching.